to iron making, steel making, and recycling. So in this block of presentation, we're going to have Sarah, Laura, and Iman who are going to present. So Sarah, the floor is yours for the first presentation on iron making.
I cannot share my screen because someone is sharing.
Can you help Ev with the...
No, the previous person needs to stop his sharing
Mohamed
because I
needs
cannot
to
share.
stop sharing.
Mohamed, can you stop sharing?
I'm trying, but
Okay. Do you see my screen?
Yes.
Okay, perfect. So good morning. I'm Sarah. I'm a second year student at Polytechnique Montreal, and I joined the university this summer in the context of an internship. So today I'm going to present to you the content of my research, which is the direct reduction of iron ore with hydrogen. So steel is part of our daily life in the shape of building, home appliance infrastructure. That steel is produced with iron extracted from hematite ore. There are two conventional routes of steelmaking. The first route is a blast furnace route, which uses coke as fuel. It leads to high amount of CO2, which contribute to global warming. And furthermore, as we all know, steel industry alone is liable of 7 to 9% of CO2 global emission. From the perspective of global warming, the steel industry is turning more into the second route, which is the electrical arc furnace route. In this internship, I cover the step before the melt shop, which is the Myriam process. The Myriam process is based on the concept of direct reduction. It consists of the removal of oxygen from hematite pellets in the shaft furnace without melting them. It uses hydrogen and carbon monoxide reducing agent, and it's less polluting than the previous route since only CO2 and H2O are produced. Go even furthermore in the sustainable development, the steel industry is moving forward green steel production. One way to achieve that could be a 100% H2 Myriam process. The hydrogen will be obtained through water electrolysis. It has many benefits. First of all, it's advantageous for Quebec, which use mainly hydroelectricity, and it's more environment friendly since the only product generated is water. However, even though it's really interesting, it has its own challenges. So in my internship, I was about to study the increase of hydrogen in the Myriam process and see the evolution in make-on reduction. Today, I start with talking about the thermophysical properties of planet. Secondly, I explain the functioning of the Myriam process. Thirdly, I show the effect of key parameters on the reduction process. And at the end of my presentation, I'm going to expose to you the challenges related to an H2 Myriam process. I try to follow some requirements to ensure the quality of the final product as the optimal functioning of a shaft furnace. They should have a high-grade iron content, with preferably above 67%, as well as low-gang mineral content. It should have a high crushing strength to prevent them turning into fine during the process, and the select narrow size pellet for avoiding bridging and clustering issues. As for the final product, it should have a degree of metallization around 93%. So this palette chosen will go through the Myriam process. The Myriam process is composed of two main equipment, the reformer and the shaft furnace. The goal of the reformer is the production of H2 and CO through the reforming of natural gas. The kinetic of the reaction are enhanced by nickel-based catalyst, and the natural gas will react with CO2 or water as a steam reforming, dry reforming, or water gap shift reaction. Some reactions may lead to carbon deposition, such as boudoir reaction and methane cracking. And as we know, carbon deposition is the main cause of the deactivation of nickel catalysts. So the reduction process will take place in the shaft furnace. At the top of the shaft furnace, the hematite ore will be fed at a storage bin, while the reducing gas enter gradually inside of the furnace. A gas-solid mass transfer occurs. So for the pellet, it's going from hematite to magnetite, from magnetite to wustite, and from wustite to metallurgical iron, also known as DRI. This DRI is sent to the melt shop where the steel will be produced. As for the carbon dioxide and the water produced, it will be recirculated at the entrance of the reformer. So we have some energy optimization. So some parameter may be should be taken into account since they may influence the reduction process, such as the size of the pellet or the present impurities. But today I choose to talk about the temperature of the reducing gas. So I did a FACSA simulation in order to validate some information that I got from this paper. I select the database FACPS, FT outside, and FS steel. And we have to pay attention to the H2CO ratio here because it's pretty similar to the ratio used in Myriam's process. So my goal is to observe the evolution of a reduction process at 4 different temperatures. At 400 degrees, we are able to observe that there is no FCC iron converted. We can only convert hematite into magnetite. Same observation goes even if we increase the temperature by 200 degrees. However, at 900 degrees, we are able to observe all steps of reduction. At low alpha values, we are able to observe the magnetite. Then at alpha around 920, we are able to convert all the worsted into FCC iron. 1000 degrees, which is the operating temperature pretty mostly used in Myriam's process, we are also able to form the FCC iron, but at an alpha slightly lower because it's alpha equal of 900. So this experiment implies that FCC iron is obtained from this reducing gas at temperature above 900 degrees. This study also emphasizes the impact of the temperature of reducing gas because it studied the influence of the temperature of reducing gas by on the conversion rate of the pellet. It's used mainly pure H2 and pure CO. We're able to observe that at temperature below 1100, pellet cannot be totally reduced by pure CO, while H2 can totally reduce them at much lower temperature. At high temperature, total conversion by both pure CO and H2 can be achieved much faster. So since we are now familiar with the reduction process, we can now outline the challenges encountered in the H2 Myriam's process. This is not an extended list of all the challenges that can be encountered, but very three that I choose. So firstly, it's related to the availability of the hydrogen. As long as natural gas and fossil fuel are available at high proportion and at low cost for the main steel producer, the H2 economy seems unlikely. The second problem is about the content of carbon in a DRI. Since, like we know, steel should have some small amount of carbon inside, but in a 100% hydrogen process, what will be the source of the carbon? And finally, the fact that we manipulate a higher amount of hydrogen make that we should be mindful about hydrogen embrittlement. Hydrogen embrittlement is defined as a degradation of mechanical properties, especially in plasticity. What happens is that the hydrogen atom dissolves at the surface of a metal. It creates some pressure inside of the metal, which often leads to a fracture of the metal. So this problem is often observed after a certain amount of time of service of the equipment. And one of the ways to prevent that is its treatment. So although this process has some challenges, the steel industry is still on transition and still moving toward that green steel production. To sum up this presentation, I would like to share my experience about my internship. So this was my first internship, and I had a lot of great opportunities all at once. First, I visit a steel factory. Then I was a participant at an hazard analysis. I also learned to use a new software, FactSage, which strengthened the knowledge I got from my classes. Also, I had caring and dynamic colleagues, which made my experience even more better. And I love researching because of the flexibility it allows in my schedule and the fact that I'm a naturally curious person. And finally, my project grew my interest for metallurgy, and I hope to work in this field in the future. So thank you for your attention.
Thank you. Sorry. Thank you, Sarah, for your presentation. We're right on time. I saw that there are a couple of questions in the chat until this presentation, so please don't be shy. You can ask your question, and we'll be pleased to answer if we're able to answer. So moving on to the next presenter.